Okay. Sorry for that start. Okay, so we are heavily into looking at integration. So we have defined it and we've seen that it's a nice solid mathematical object, just like the derivative is. And we can think of it, so the derivative, we think of that as the rate of change and as the slope of a function. And we've got the integral, which is the total change, so like the accumulation, and it's the area underneath the curve. So two mathematical objects, both defined by some kind of limiting process. So with the derivatives, it's rise over run. We make intervals smaller and smaller and smaller. Integral is adding up all these rectangles where the widths of the rectangles get narrower and narrower and narrower. Okay. Okay. And so what we're going to do today is just hammer down what the actual connection is between the two things. And that is a thing known as the fundamental theorem of calculus. So you know it's important because we call it fundamental. And, oops. And there it is, up there. So this relates the derivative and the integral. Actually, the fundamental theorem of calculus comes in two forms. We'll only be worrying about one form. So the form that we're going to worry about is what happens when you integrate a derivative. The other form of the theorem tells us what happens when you take the derivative of an integral. We'll get to that later. And it is right that if you integrate a rate of change, what you get is the total change. So we've already seen that before. So now we're just sort of putting it down in a concrete form. Okay, so the definite integral of the derivative of a function is the total change in the function. Right, so let's see what we're doing here. So here is a derivative, it's a rate of change. We're integrating it, and it's the total change, right? It's what the function is at b minus what the function is at a. And so notice that there are two different functions here. There's f prime, which is the rate of change, and there's f, which is the function itself. And you know that all throughout the course, I've asked you questions about, here's the rate of change, what's the function for? Here's the function, what's the rate of change? So all through the course, I've emphasized that these are two different things. And here we see them both in one kind of picture, one formula. And so you can see why it's important to keep them different from one another. Okay, so I think the easiest way to figure this out is by actually doing a nice little example. Okay, so here is a graph of a rate of change. Okay, so what's it saying? It's saying that we start out, we're not moving for the first time period. We slowly go backwards at a linear rate till we're going at -1 unit for whatever. So we keep at that steady negative speed, and then we turn around and we accelerate at a positive rate, from going backwards to going forwards, and then we go at that constant rate up here for a 1 unit of whatever it is. Okay, so I'm giving you the rate of change So that's not enough to actually figure out what f is, right? Because when we integrate, we just get the total change. So we need a starting point. So we need to know where we start at. So this 2 here is an additional piece of information. You can't get that from here. Okay, so let's that's at time 0. Okay, now where are we at point 1? Okay, so when we look at this, we know that the change in f from 1 to 0 is going to be the integral between 0 and 1. So we look at that. What's the integral of this function between 0 and 1? What's the area of this little triangle here? It's 1/2. It's below the x-axis. So therefore, the change is minus 1/2. So we must be at 1.5. Okay, between 1 and 2, we've got a constant rate of change, negative rate of change. The rate of change is -1. So the change from 1 to 2 is -1. So we must be at 1/2. At 3, right, from here to here, we're still at this -1. So we're going to be at -1/2. At 4, oops, sorry, people at home can't see that. What was that? I was at 4, right? At 4, all of a sudden we started slowing down the rate at which we're going backwards. Okay. Now the area, we've got a triangle instead of a rectangle. That area is 1/2. It's below, it's still minus 1/2. So we're -1. Between 4 and 5, it's still 1/2, but it's above now, it's positive. So it's -1/2. And then finally, from 5 to 6, we're going at a rate of 1. So we're going to increase 1 unit from 5 to 6. So it's going to be 1/2. Okay. And so that tells us then that the total integral of this function over that period 0 to 6 is going to be -1.5, because the total change was -1.5. Okay. Think about this one. This example just basically encapsulates everything we're going to be doing today. So if we know the derivative, we know how things are changing. If we know where we start from and we know the derivative, then since we know how things have changed, we can add that to where we started from to figure out where we ended up. The basic. Okay, so let's just apply this to some kind of economic situation. So this is, we've done all this through the class. We've looked at cost and revenue. That's been a basic example for us. So what do we know? We know that the derivative of cost is marginal cost. And we know that the intercept for the cost function is the fixed cost. That's exactly the same situation here, right? If we know the marginal cost and the fixed cost, we can figure out the cost. We can use the marginal cost to figure out what the total change in cost is. And if we know the fixed cost, we just add the change in cost to the fixed cost, the change in cost, i.e. variable costs, we get the total cost. Okay, and so this is just translating that function, this formula that we had here, to cost. All right, so we're taking the derivative of the integral of the marginal cost function. Since marginal cost is the derivative of cost, when we integrate marginal cost, then we're going to get the total change in cost. Right, so that's going to be CB minus CA, where A and B are the bounds of the integral. Another formula we get. What is the total variable cost? Well, it's going to be the integral of marginal cost from 0 to wherever we're trying to figure out the total variable cost is. And then finally, we know that the total cost is fixed cost plus total variable cost. And we've got formulas for each of these, right? Fixed cost is just the intercept for the cost function. So that's C0. Total variable cost is just the integral of the marginal cost function. And that gives us a nice formula. So this formula here is just another way, is just putting the formula for the fundamental theorem of calculus and just translating it to the cost function. Okay, so we can do another problem, just like this one. So this one was kind of abstract kind of problem. This one is something a little bit more concrete, it's the cost. So we can do the same thing. Okay. Our table is now going to have Q, marginal cost, and we want to figure out total costs. So here we've got 0, was it every 100 up to 6. Oh, okay, so let's just do the integration. So we've got okay. So this problem that we did back here was a graphical problem. Now we're going to do a numerical problem. So we want to integrate this function here. Okay, and we know how to do that. We do a Riemann sum. So if we do it using the left-hand sum, then we're just going to add up a bunch of rectangles using the left-hand point. So what's the width of the rectangles in this situation here? 100. That difference there. And the sum is going to be 25 plus 20 plus 18 plus 22 plus 28 plus 35. And we don't include 45, right? Because we're going to count this interval twice. And so that's what, 45, 55, 63, 85, 113, 148. So the left-hand sum is this. The right-hand sum is 100. Now it's 20 plus 18 plus 22 plus 28 plus 35 plus 45, which equals, well, this is just 20 more than this. I think 16,800. And so our estimate then of the variable cost for 600 units is $15,800. If we're told that the fixed cost is 10,000, then the total cost for producing 600 units is then going to be $25,800. And actually, I saw that I didn't answer the question there, right? They actually asked, what would be the total cost of producing 400? Well, then we just go to this far here, right? So we would only do this amount, which would be, sorry for this, I hate it when people do this. We get 45, 53, 85, it would be 8,500, whereas this would be 38, 60, 88, the 8,800. So the variable cost for 400 units would be 8,000, and now the average of this would be 650. We still have fixed cost of 10,000. That doesn't change just because we're doing 400 units, and so that would be $18,650. So what would be the cost, the increase to this cost if we could decide to produce 401 units? How much extra money would that cost? Yeah, we know what the marginal cost at 400 is. That's exactly approximately, sorry, I shouldn't say exactly approximately, that's approximately the cost of producing that extra unit. That's what that marginal cost means. Let's just go back a second. Here's another question. Here's another graph. So I'm graphing f prime again. And let's say f prime looks like this. Okay. One, two, three, four, five, six. Okay, so here's a question. Compare F6 to F0. Which number is going to be bigger? If this is the derivative, if this is the graph of the derivative. And why is that? Right. So this area here, this interval here, sorry, is going to be F6 minus F0. That's going to be the total change. You can see from the picture that that's going to be a negative amount. So that means F6 minus F0 is negative, which means that F0 is bigger than F6. Okay. We can get problems where we have to approximate what the area is. So for example, remember in that first problem, I gave you something with straight lines. So it's possible to figure out things exactly because you can figure out rectangles and circles. But you could be given a problem like this, where you're given a grid of points. Okay, and so this is 0, 1, 2, 3, 4, 5, 6. And so this is f prime of t, for example. And so if we're going to integrate f prime of t between 0 and 6, we've seen these kind of problems before. It's then just like, okay, we start adding up squares, rectangles, whatever. And then we start, first we do the whole ones, and then we go through, we say, well, this plus this looks like 15. This, and this looks like 16. This and this looks like 17. And so this looks like just like under 18, so maybe it's 17 3/4 squares. And then we figure out what each of the squares is worth. And that'll give you the integral. So we've seen those kind of problems. Okay. Okay. So here are some velocity graphs. Okay, and so we know that if we've got velocity graphs, we know that the area is going to give us distance traveled, and the slopes are going to give us acceleration. So what is the question asking? Order the graphs in terms of the distance traveled in 4 seconds, greatest to least. Okay, so let's interpret what that means. So distance traveled in 4 seconds, if it's a velocity curve, that means it's asking for what is the area underneath the curve between 0 and 4. So that means we've got to figure out what those areas are. So, anyone like to hazard a guess which one has the greatest area? Everyone agree with that? Right? We can tell because, right, it kind of ends, ends at the same place, but this starts thing How do we compare these two things? They're equal to each other. Very good. Yep. So it's just flipped, isn't it? So this is a trapezoid. This is a trapezoid. If I take this trapezoid and flip it over, I can put it on top of that. So the area is exactly the same. Okay. So the answer to this is D. These two are the greatest distance, and that's comes in third. Okay, here's a little bit of a different one. So here is a graph of velocity versus time. And here's 4 candidates for position versus time. So, which one of these could be the position for this? So remember how we had these problems where we went the other way around, right? Where I gave you a function and I told you which of these is derivative. Now it's the inverse problem. I give you the derivative. Which one of these could have been the function? So this is velocity, which one is position? So how do we went about doing this? Okay, so what can you tell me about this velocity here? It's positive. So if the velocity is positive, what does that tell us about position? No. If the velocity is positive, what does that mean about position? If the derivative is positive, what does that tell us about the function? This is one of the first things we discussed when we talked about derivatives. It's increasing. So straight away, we can eliminate 2 and 3. Right? Because this thing here and there has a negative velocity. Okay. Now, so we're looking for something which is an increased function. Here, the derivative is 0. So what does that mean about the function? The rate of change is 0, so it's flat. Okay, that doesn't eliminate anything because both of these, right? And so what's happening? So it's becoming steeper and steeper, and then it's straight for a while, and then it gets steeper and steeper. Still can't tell the difference. In fact, these two things have the same velocity, right? Why is that? What geometrically tells you that these have the same derivative? They have the same slopes, so therefore the curves are what? What do we call that? They're parallel, right? These two things are parallel. Actually, these two things are parallel as well, right? So the answer is 2 and 4. No, sorry, 1 and 4. Sorry, 1 and 4. So the answer was E. Okay, so here's another one. So hopefully, so I'll give you a second to have a look at that and you try and figure out. So remember, think about when's it increasing, when's it decreasing, when's it flat. None of those are are parallel, so there's just one answer to this problem. It would be B. So you say B. Sorry, what did you say? B. 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 So what's it doing? So first the derivative is positive, then the derivative is negative. So what's it doing? Can't be B, right? So what's the function doing here? Well, the velocity is positive.
It's increasing and then decreasing.
It's increasing, then decreasing.
So A.
Yeah, there's only one candidate. A is the answer for that. Okay, interesting. Okay, now I give you two rates of change. Okay, so we're talking about people getting sick. Okay, so F is the rate at which people are getting sick. G is the rate at which they're getting better. Okay, so some people get sick, and so it's not the same people, right? So we've got a population, some proportion of them get sick, and some proportion who is badly sick get better. Okay. So which one of these represents the number of people sick during that period? This one's a little bit trickier, right? So what is the derivative of the number of people getting sick going to be? What is it in terms of F and G? F minus G, right? So we've got people getting sick. So let's think of them as some quantity, right? People are entering here, and they're entering at the rate of F, and they're leaving by getting better, and they're leaving at the rate of G. So the derivative of sick is F minus G. So in this period here, what can you tell me about the graph of the people being sick? Is it increasing or decreasing? It's increasing, right? Because F is bigger than G. What's happening at this point here? The graph. It's flat, right? Because the rate of change is 0. As many people are getting sick or it's getting better. So that we're going to expect an increase flat at 12. And then what's going to happen here? It's going to go down because people are getting better. And we're expecting it, right, to get steeper and steeper. Okay, so what are candidates? Okay. These two totally don't work at all, right? And so the difference is it's going to be either B or D. Both of them have the thing where they increase, flat, and then decrease. And so we've just now got to study it more carefully because they are different, right? Yeah, yeah. We can see that this sort of goes off steeper, which is kind of more consistent with this. And I think it reaches its flat point at the right time too. So there's a couple of clues there that can tell you that B is the right answer.
So why is F, like when we at the beginning when we said it was increasing, why would it be increasing? Because like if it's F minus G, F is decreasing in that.
Right, no. F is the rate of change. Right? F is the rate at which people are getting sick. So F minus G is the rate at which the sick population is changing. So if F is bigger than G, the rate is positive. That means it's increasing. So don't get confused between the rate and the thing itself. Just because F is decreasing doesn't mean the number of people getting sick is decreasing. That just means the rate at which people are getting sick are decreasing. So even though F is decreasing, more and more people are getting sick because this is positive. This is derivative. The derivative is positive, so therefore it's increasing. Okay, so that's, again and again, I ask those kind of questions. Don't get confused between the rate and the thing. The rate, if the rate is positive, the thing is increasing. Even if the rate is going down, as long as it's positive, the thing is going to be increasing. Okay. Here's an economics question. The fixed cost is $3,000. What is the total cost of producing 5,000 items?
Could be B. I don't know. Could be C.
C? You did 6 times 5,000, didn't you? Why is that not right? I agree, you do 6 times 5,000. That's going to be the area of this square. What's the area of the triangle? 15,000, right? So 15,000 is the variable cost. Add 3,000, you get $18,000. Okay, I can tell without even looking much closely that the answer is going to be E, right? Because you had 15,000 and 18,000. They were the only two separated by $3,000. So it had to, just on principle, there had to be that one. Yeah, everyone else okay with this question? Okay. So here is a function, and this is its derivative. So what represents f of b minus f of a? Right, the fundamental theorem of calculus says that f of b minus f of a is going to be the integral of the derivative between a and b. Okay. Which one of these is the integral between a and b? Yeah. Yeah. Everything else is just not. Okay, that was not a hard one at all. This is just the fundamental theorem of calculus. The difference between this and this, the difference between those two heights is going to equal that area of the derivative between a and b. Right, and we see the relationship between this and its derivative, right? We see it's increasing. You see the derivative is positive. Here it's decreasing. You see the derivative is negative. Okay. That sounds like enough for today.